All right. Well, hey everybody. We have some people tuning in on YouTube who can't make the time. So thank you for watching. Today we'll be going over chapter 0 of Hatcher's Algebraic Topology. So this is kind of starting a new seminar for what I usually put on my YouTube channel, which is Algebraic Geometry. But some friends who took topology with me all wanted to study algebraic topology after we finished our exams, and so we went and we got Hatcher, and we're going to read through it. And so we have kind of like a reading plan that I'll talk about in a second, and we'll be following it just kind of to the letter. So yeah, today we'll be going over chapter 0, which isn't too bad. It's just kind of like some underlying notions about homotopy and then like cell complexes. And then lecture 2 through 8, we will split up on chapter 1. And so that gives us basically 7 lectures, which is like a week, to go through everything in chapter 1. And of course, this is without this is without no small amount of work on the side to go through homework. And then chapter 2 will start probably the week after Christmas on homology. That'll be lectures 9 through 18. Although I expect that to potentially go a little slower, but who knows? We might just have to kind of insert some category theory stuff that we didn't really get to cover in our topology class, because that's pretty important. But yeah, I mean, it should be like one extra lecture kind of thing. And then if we get to co-homology groups, I'll be very happy and also very surprised. So that's the plan. And without further ado, we'll go ahead and start. Let me start sharing my screen. Like with the art and reading seminar, I'm planning to basically lecture unless someone else wants to lecture. And it won't really be a lecture because I don't know algebraic topology. It'll just be me reading out of a book and writing things down and saying things until it kind of makes sense and everybody's happy. So Jorge, is that good for you?
Yes, that works. Sounds good.
Okay. So chapter 0 is fairly short, and a lot of it is stuff that you and I have kind of already seen. So it's called Underlying Geometric Notions. The aim of this short preliminary chapter is to introduce a few of the most common geometric concepts and constructions in algebraic topology. So the exposition is somewhat informal with no theorems or proofs until the last few pages. It should be read in the informal spirit, skipping bits here and there, and it's basically just defining some things. Maps between spaces are always continuous unless otherwise stated. Okay, and so the first section is on homotopy and homotopy type. So one of the main ideas of algebraic topology is to consider two spaces to be equivalent if they have the same shape in a sense that is much broader than homeomorphism. To take an everyday example, the letters of the alphabet can be written either as a union of finitely many straight and curved line segments or in thickened forms that are compact subsurfaces of the plane bounded by simple closed curves. And I guess because we don't have the ability for me to show, kind of what he does is like bubble text versus, and then it's that kind of thing. And so it's like saying, okay, you could write this 2 different ways, sort of, and so on. In each case, the thin letter is a subspace of the thick layer, and then we can continuously shrink the thick layer into the thin one. A nice way to do this is to decompose a thick letter, call it X, into line segments connecting each point on the outer boundary of X to a unique point on the thin subletter X, as indicated in the figure. And so this is kind of the idea of taking like a straight line from the boundary to the thick letter right? And identifying points on the boundary of this outer space to like points on the boundary of the subspace. Then we can shrink the large layer to the thin layer by sliding each point of x, basically in what we're familiar with as like straight line homotopy. And so we can think of the shrinking process as taking place over a time interval from 0 to 1. And then it defines a family of functions parameterized by t that go from 0 to 1. And at time 0, it is this outer layer, and at time t, it's the inner layer. And this is kind of the fundamental notion of homotopy. So naturally, we would like to this function family to depend continuously on both t and x. And this will be true if we have each kind of like difference between letters move along its line segment at constant speed so as to reach its image point at t equals 1, whereas the points in the smaller letter are stationary. And so this leads to a general kind of example called a deformation retraction. So definition, deformation, retraction of a space X onto a subspace A is a family of maps. So I guess it's really a deformation retraction. A deformation retraction of X onto A is a family of maps f sub t from X to X, t in the unit interval 0 to 1, which we're going to denote by I, such that f naught is equal to the identity map on X. And then f1 of X is equal to A. And that the restriction map, I think that's restriction map of T on A is the identity. That's how I've seen that used. So I think that makes sense. Does that make sense? Like FT bar A here, that means like restriction map at A.
Oh, yeah.
Yeah.
I remember.
Yeah. So it's easy to produce more examples similar to the letter examples with the deformation retraction FT as defined here, obtained by sliding along line segments. So he has some kind of cool figures that I'm not good enough at drawing to really replicate. But basically, you can deform a Mobius band into a two-hole torus. And so it kind of goes. I can't draw that. I would be lying if I said I could. But in these examples, the structure gives rise to the deformation retraction. In all of these examples, the structure that gives rise to the deformation retraction can be described by means of the following definition. For a map X to Y, so let F from X to Y, the mapping cylinder MF is the quotient space of the disjoint union X across the unit interval disjoint Y. obtained by identifying x comma 1 in x cross I with f of x in y. And so disjoint union, I hope I'm going to look up a more intuitive definition than the one that immediately comes to mind from category theory, because I know that that is not the best way to do that. So a disjoint union keeps elements separate. So basically, like example of a disjoint union. Disjoint. So basically, so 1, 2 coproduct or disjoint union 2, 3 is equal to basically the pairs 1 comma the first set, 2 comma the first set, and then 2 comma the second set, and 3 comma the second set. And so then I'm pretty sure, yeah. So there's this formalization in category theory that's particularly useful, called the product, which basically says that you have x and you have y that factor through x and y, and that everything that factors down to x or down to y factors uniquely through x product y, which is of course the union. But then the coproduct, which is in the category of sets, I believe, the disjoint union, it's the dual of the product, meaning that when you have these things, it flows like this. So everything factors through the product, and then this is where we get the notion of this is the definition that I was going to pull out that I was kind of trying to avoid. But basically, by using the coproduct, it says, okay, everything factors through the product. And so you want to identify the element with its original set. And that's our notion of factorization. So going back to this definition, so the disjoint union of x with the unit interval and y, and then the mapping cylinder being this quotient space where we identify x comma 1 with f of x. I'm a little... So it's the quotient space of the disjoint union. So I guess we're chopping everything in x product I up. Disjoint union that with y, and then we map things from x comma I into the disjoint union with y by identifying them as pairs of like x comma f of x. And then this is, I guess, identified with x comma 1 in the quotient space. Does that seem like I'm reading this definition right, Jorge?
Yeah.
Okay. I will add that I'm very okay with being wrong, and it's very likely that sometimes I'm wrong. So if there's something that like just doesn't seem like it is right, then please say that.
All right, I will.
So, yeah. And I guess while I'm at it, I made this very bold claim that the coproduct is the disjoint union in the category of sets. Let me Google that. Is coproduct equal union in category sets? Yes, it is the disjoint union in the category of sets. Okay, so since that's what we're really working on here, I think that that's okay. And so this is equal to this in set. Okay. So yeah, the mapping cylinder. Oh, and he has a picture for this. Maybe I should have started with the picture. So picture of mapping cylinder. So if we have, wow, that like did not do an ellipse. And this is X product I. Then we have some like sub image where this is f of, or lower f, lower f x, and then this is y. And so then the mapping cylinder identifies like a point down. Like that, kind of. And so it's mapping the whole cylinder down. So does that like pictorially make sense?
I think so. I'm not sure. I'm following, but
Yeah, so this is MF. And so the mapping cylinder is the quotient space where we identify like everything on f of x um, at some point like on this boundary. So in the letter example that I gave like way at the start, let's take like A. And then let's do so the space X is the outer boundary of the thick layer. So the boundary of thick is X. And then Y is the thin layer. And then F from X to Y sends each outer point of this like that. That's F of X, or like equivalently that. to its inner endpoint. I guess maybe I should move y. There we go. Now it makes sense. So like functionally, I'm pretty sure this is just like how Dr. Bush kind of taught us to think about homotopy.
Oh no, I had to learn most of the homotopy part from Monkeras. Like I wasn't paying that much attention to Dr. Bush.
Yeah. Yeah, I mean we didn't get to spend too much time on it, but
Yeah.
I mean I think just the key idea is that the actual part where we're sliding things down, like the unit interval, that's the mapping cylinder. And then we identify everything with its endpoint on f of x. So like I think almost an arithmetic example would be easier if we're like considering the straight line homotopy, like on f of x equals 0, for I don't know, whatever, and then g of x is equal to x squared. Then the homotopy, like from f to g by h on and by x we really mean the real numbers here. Then this line just kind of identifies itself with like the points on. I'll draw a picture before I find the homotopy. Yeah. So it's kind of like going here to here. And then like this orange part is the mapping cylinder. And then the way like in terms of Dr. Bush, then I think then that would just be the homotopy H.
Yeah, that makes sense. I remember that.
Yeah. Oh yeah, and then it goes on to the next page to say deformation retraction is a special case of the general notion of a homotopy. Okay, so we were on the right track. I think
Yeah.
my bad confused there. Yeah. So yeah, it's just like a general homotopy. And we already are familiar with the notion of homotopy, but I'll write it out just for the sake of having the notes. So definition, basically, a homotopy is a family of maps ft from x into y, with t and I, such that f from x across the unit interval to y has f of x comma t is equal to ft of x is continuous. And then two maps are homotopic if there's a homotopy f sub t connecting them. So two maps are homotopic if there is a homotopy f sub t of x connecting them. I'm just going to clarify this t here. That's not a very nice t. Yeah. So in these terms, a deformation retraction of X onto a subspace A is a homotopy of the identity map to a retraction map. So basically, deformation retractions is really just, you know, the notion of the identity map being homotopic to the restriction map on A. From a more formal viewpoint, a retraction is a map with r squared equals r. That's interesting. A retraction is a map r from x to x with r squared equals r. That's really weird. So this equation says that r is the identity on its image. That's kind of interesting. That's like a very neat way to view it. So r is the identity on its image. So not all retractions come from deformation retractions. For example, every space retracts onto any point via the map sending all of x to that point. But a space that deformation retracts onto a point must certainly be path connected, since a deformation retraction of x to a point gives a path joining each point to the point that we've picked out, x naught. It is less trivial to show that there are path-connected spaces that do not deformation retract onto a point. One would expect this to be the case for letters with holes. And so in chapter 1, we developed techniques to prove this, but that has to do with like the fundamental group and stuff that we've talked about. So a homotopy that gives a deformation retraction of X onto a subspace has the property that its restriction map is the identity for all T. So basically, like, for any subspace that we pick, it's contractible, is I think the way to put it in terms of like what you and I are familiar with. And like this makes sense. X is this space, you know, that has effectively like what we're saying is no holes, right? Then we can pick out any subspace A and it's still contractible to a base point. As long as we pick the base point to like lie within A. But even if we didn't, like we could also just pick this and then this is homotopic by straight line homotopy.
That's all the thing that we learn in complex analysis.
Yeah, I mean it's pretty much like how you get a lot of like the nicer integrals in complex analysis. Yeah. So a homotopy that gives a deformation retraction of X onto a subspace. Yeah, oh, I literally just said that. Okay. In general, a homotopy whose restriction to a subspace is independent of T is called a homotopy relative to A. So this is an important definition. A Homotopy. I'm going to abbreviate this HT from now on. F sub t from X to Y, which has ft restricted to A, is independent of t, is called a homotopy relative to A, or HT rel A. Thus, a deformation retraction of X onto A is a homotopy relative to A from the identity map to a retraction of X onto A. And I think we can talk about this now that all of our finals are graded, but this was like basically the thing about showing that like in path connected spaces, the identity map is homotopic to any two functions that are injective into a space.
What kind of spaces? Sorry, what kind of spaces do you say?
Like remember the problem on the exam where it was like if you have any space and any two maps that go into the other space, then you have like and this space is path connected. First we had to show it was contractible, and then we had to show that because it's contractible, this map is homotopic to the identity map, which is homotopic to the other map, and so any two maps into the space are homotopic.
Yeah, I was confused with the second part of showing that it's contractible or not.
Yeah, it was.
Right?
No, it is.
Yes.
Yeah, it is because brief detour. But like, okay, if it's contractible, right, then that means that if this is our base point, any loop that we take contracts to the base point. And so if we have any two functions like that act as loops in here looking like this, right? Those both contract to the base point. And since they both contract to the base point, you just have to find a homotopy that contracts to the base point and then contracts out to the other function. And so it's a little complicated. It's really funny. I like kept looking for a straight line homotopy to do it, and then I realized that wouldn't work, and so then I ended up having to make a Lagrange polynomial. So I don't know. It worked eventually, and I got the problem right. But yeah, so that's kind of like what we're talking about with like a deformation retraction being homotopy relative to subspaces. Like the identity map on the point is just like we can move any point x naught to the base point. And then since we can move any point x naught to the base point, if we consider like a function like this that is a loop, right, by definition, then we can move that over to the base point. And then we can use the identity map on it. But then we can do the same thing for some other function and move that over. And then we can concatenate those two loops with loop addition. And then they both add up to be the base point.
Just to make sure we're talking about the same problem, was that the problem with the space with a hole in the origin?
No, that was a different one.
Okay.
That was a fun one though. Yeah, mine is something along the lines of if you have a space that is contractible or a space that is path connected, show that it's contractible.
Oh, okay. Yeah, no, I was confused. Yeah, no, that makes sense.
And then show that any two functions into that space are homotopic. I think that was the problem setup. Anyway. Back to the content though. So if a space X deformation retracts onto a subspace via a retraction from X to X, then Then if R denotes the resulting retraction and I is an inclusion map, oh, I should write this. I'm going to put this as like a lemma. Okay, so if X has a deformation retraction onto A contained in X as a subspace via the homotopy F sub T of X, and if R from X to A is the retraction, and I from A to X is the inclusion map, then R composed with the inclusion map is equal to the identity map on A. So basically, if we have like a homotopy retraction into A, and then we have an inclusion map back to X. Oh, this isn't the identity on A. This is A to X, X. No, it is the identity map on A. Yeah, okay. I did that right the first time. It gives us the identity map on A. And so the picture here is like, if we pick out A here, and then we have this loop that goes down maybe by like FT. So like that. Then basically we can, that is, or no, I guess this wouldn't be FT, that would be the retraction R. So that's R from X to A. And then A back to X goes this way. That's I. Then I composed with R says we send this map over and then we retract it back. And then that's the identity map on like a loop. I don't even think this is restricted to a loop at this point. I've been saying that everything is a loop because that's like kind of where we're going. But I don't even think that we're like restricted to the notion of like loops or base points right now. Does this all make sense?
Yep. Yes.
Okay. Starting to think we might not make it through all of chapter 0 today. So I'm gonna speed up on the homotopy stuff that we both already know. So to generalize the situation, a map is called a homotopy equivalence if we have something where we're basically, okay, I guess this is a definition that we should know. So F from X to Y is a homotopy equivalence. If there exists a map G from Y to X with FG homotopic to the identity on Y and GF homotopic to the identity on X. And then basically if a homotopy equivalence exists, then X and Y are considered to be homotopy equivalent and have the same type. So it is true in general that two spaces are homotopy equivalent if and only if there exists a third space containing both X and Y as deformation retracts. For the less trivial implication, one can take Z, this other space, to be the mapping cylinder of any homotopy equivalence. And we observed previously that the mapping cylinder deformation retracts to the codomain of the original function. So what needs to be proved after that to show this is that the mapping cylinder also deformation retracts to its other end, x, if f is a homotopy equivalence. And so I think that gets into like just without loss of generality kind of thing.
Wait, intuitively, so this means that two spaces are homotopy equivalent. We can deform one into the other.
Yep. Yeah. That's basically what this means.
Is that stronger than being homeomorphic?
It's weaker.
Weaker.
So homeomorphic means that we have a continuous map in the category of topologies that's bijective and bicontinuous, and admits an inverse on the left and right. And so that is a stronger thing because it means that we can identify open subsets with open subsets.
So if two spaces are homotopy equivalent, they are homeomorphic, right? Automatically.
I don't
because
think
F,
so.
in this case, F should be an homomorphism, right?
If two topological spaces are homotopic, are they homeomorphic? I don't think so. Yeah, because like for example, the trivial topology is homeomorphic to is homotopic to R, right? Because they're both path connected, but they're definitely not homeomorphic because like R with the standard topology has infinitely many subsets, and then like the trivial subset is just itself.
Okay.
So homeomorphic, I think homeomorphic definitely implies homotopic. Does homeomorphic imply homotopic? Yes. If two spaces are homeomorphic, they are also homotopic.
Okay.
Yeah. And so it's, I mean, that makes sense. Like that just means that they have the same structure. I maybe should have been a little more confident when I said that. Yeah. Does that make sense?
Yes.
Awesome. Okay, so a space having the homotopy type of a point is called contractible. So definition, if a space has the homotopy type of a point, it is contractible. And we're already familiar with that definition, so no need to like. This amounts to requiring that the identity map of the space be what is called null homotopic. So a map is null homotopic if it is homotopic to a constant map. And this was one of the problems that showed up on our final exam, was showing that basically a space is contractible if its identity map is null homotopic.
Yeah.
And that was the problem I was talking about, or part of it. Yeah. Let us describe now an example of a two-dimensional subspace of R3 known as the house with two rooms, which is contractible, but not in any obvious way. Wow, that sucks. I cannot draw that.
What is it?
I'm gonna, I guess, just try and show it. But I have the blur on, so maybe I'll need to, I need to de-blur my camera. All right. So this is the thing. And so this is contractible, but not in an obvious way. Yeah. This is an interesting example, but it really requires you to have the picture. So I'm going to skip this and bump it to, you should get a copy of the textbook and take a look at that.
What's the example about?
Huh?
What's the example about?
It's just showing that that space in the diagram is contractible. So we can pick a based point and any loop is gonna go there, which really seems counterintuitive, but it's, I guess, because of the way that the hallways for dropping in lines up for changing floors. You can basically construct a loop around, and then you can like loop it over and over the two elevators, and you get like path in, and then it's contractible. So that's pretty interesting. Okay, so the next section is called cell complexes. Towards cell complexes. A familiar way of constructing the torus, which is the product of the sphere with itself, is by identifying opposite sides of a square. So more generally, an orientable surface of genus G can be constructed from a polygon with 4G sides by identifying pairs of edges. So I guess remark is maybe how I'm going to put this. An orientable surface MG genus G can be constructed from a polygon with 4G sides. And so as an example, and I'll do my best to draw, maybe I need to take art lessons or something to really be able to do this. So to construct the torus, if we orient these two sides and we glue them together in the following way, then we end up getting a torus. Maybe I'll make that deeper so that it's clear that it's really a torus. Wow, okay. Yeah, art school I am not destined for. Hopefully that's clear that that's a donut. They have some more complicated examples that I definitely can't draw. But basically there's like one that you can make with an octagon that is the two-holed torus. And it basically comes from, you leave this part of the construction the same. So I guess let me do this and this. But yeah, maybe I can draw it. I just have to be careful. Nope, that's a hexagon. And I might color code this instead of doing the letters. So, nope, that's reversed orientation. So we flip that over, we flip that, nope, that needs to be a different color. And then B and D, so all of them switch directions actually. But then the key part is that the green and the blue have the same direction, and then the orange and the yellow have the same direction. So this is this thing, this is this thing. Is that clear how that like glues together?
Yeah.
Okay. So then basically the 4G edges of the polygon that we described to like make these spaces become a union of the 2G circles in the surface, all intersecting at a point. So then the interior of the polygon can be thought of as an open disk, or a 2-cell. So an open disk is a 2-cell. I'm just going to write that as convention. So open disk equals 2-cell attached to the union of the 2G circles. One can also regard the union of the circles as being obtained from their common point of intersection by attaching 2G open arcs or 1-cells. So an open arc is a 1-cell. So thus
What
the
do you
surface
mean again? By cell? By two cell?
really know.
Like something that is like a donut?
You know, that's a great question, dude. I'm not sure yet. He kind of uses the notation. I think he means. I'm gonna Google this. I think it might be how many intersections the lines of a polygon have. Right? Like if you think of like if you take a cube, I'm guessing that that's going to be a 3-cell. Like a rectangle is going to be a three. Sorry, not a rectangle. No, it would be a triangle. Because like a circle intersects itself in one place, a triangle intersects in 3 places, but you can't fold over a triangle. Can you? No, because it has to be divisible by 4, so it has to be in units of 2. So it can either be a 1-cell, 2-cell, or a 4-cell. Would that be the next point? Because then you have a square, then you can make the torus. Hold on. I'm going to Google this. What is a cell topology? So it defines relationships like neighbor. In advanced math, algebraic topology, it describes building complex spaces from simple cells like points, lines, disks glued together. Focuses on the skeleton and how higher dimensional cells attach to lower ones. Okay. So maybe it'll actually be clear from construction of a polygon. So you start with a point and you attach open arcs to this point, and then you attach an open disk. So to build a surface, take a base point, attach 1-cells, then attach 2-cells, or a 2-cell. So you add lines and then you attach an open disk.
Mm-hmm.
A natural generalization of this is to construct a space by the following procedure. So start with a discrete set of 0-cells. So 1, start with x0, a discrete set of 0-cells. 2, form the end skeleton. The end skeleton. And I guess the end skeleton is xn. From x n minus 1 by attaching n cells denoted by, this is terrible notation. What? There's no way people use this. N cells e alpha to the n via maps phi alpha from S, from the sphere n minus 1, the x n minus 1. And so then x to the n is the quotient space of the disjoint union x to the n minus 1 coproduct alpha dn alpha, and he defines what dn alpha is in a second, of x to the n minus 1 with, wow, I don't think I've ever written W that badly, with a collection of n disks D and alpha. So they're n disks under the identification x is identified with phi alpha of x for x in the boundary of the n disk. So he doesn't clarify this, but this means boundary. So then as a set, don't worry, we're going to unpack this. This is not something to breeze past. Xn is xn minus 1 coproduct over alpha. The n disks. So, yeah, that's interesting. So the e to the n alpha is an open n disk, and I don't think that's clear. Open n disk.
No, I'm confused too.
Yeah, so that just goes from like 0 to everything all at once. And then this is endowed basically with the subspace topology. Yeah. So if you, it's worth noting, right? You don't ever have to have a finite n on this. You could have an infinite dimensional cell complex. And so open sets in that cell complex are sets which intersect the x to the n complex for each n. So basically, if n goes off to infinity, A is open in x to the n, or rather, it's open in x if and only if A intersect x to the n is open in x to the n for every n in 1 to infinity. And I think that this will actually be very important later. I have something of a hunch from algebraic geometry intuition that that this is going to be incredibly important for homology later. Yeah. So a space X constructed this way is a CW complex or a cell complex. An explanation of the letters CW is given in the appendix, where a number of basic topological properties of cell complexes are proved. Okay, I'm kind of thinking that we should jump to the appendix and do the stuff about cell complexes. Call me crazy, but I don't think I'm ready to move on from this yet. But he does have some examples. So actually, maybe it's worth doing the examples before we jump to the stuff with point set topology about cell complexes. There is one definition that's important. The dimension of a space X, where X is represented by a cell complex, is the max. Is it the max or the sub? I think it's just the max. Dimension of cells of X. Yeah, so let's. Okay. I do want to think about this more, but I'm wondering if examples are going to help or if the appendix is going to help. So I'm going to look at the appendix. Topology of cell complexes.
Yeah, let's cover the appendix.
Yeah, I think that'll be ideal. So, it's worth also noting here. So this is called, this stuff in orange that I'm moving around is called the weak topology. And it is the union over n of x to the n. Condition 3 is superfluous when x is finite dimensional. Yeah. So each cell, so jumping into the appendix, has a characteristic map, which is defined by the composition so characteristic map. Characteristic. So phi from alpha is defined by the composition dn alpha, which injects into x to the n minus 1 coproduct over alpha dn minus 1 alpha, which has a map into x to the n, which it injects into x. I'm going to add a thing in the notation. So I realize that I've used some conventions so far that some people don't use. So this means is open in, and this is nice because it lets you say, like, if you just have a set, you can clarify subset, open set, and elements all with like the same notation without having to say x and like tau or something. And then an arrow like this is a surjective map. And then a hooked arrow, which is we've used in the diagram below, is an injective map. And so this is an injection here, and this is an injection here. And then a bijective map.
Sorry.
Huh?
What's a characteristic map?
Well, each cell each cell has a characteristic map. So this is defined on E alpha X. Nope, E alpha N. That was so close. This is continuous since it's a composition of continuous maps, but it doesn't tell me what it is yet. So an alternative way, so here we described the topology on X for non-finite n. An alternative way to describe that topology is to say that a set is open if and only if the inverse image of the characteristic map of a cell on an open subset is open in each n disk for each characteristic map. I think there must be some intuition here, but I think some of this is actually just kind of making a leap over. I need to plug in my iPad.
But the things that we're mapping are topological spaces, right? We're not in groups yet, right?
Yeah, so we are dealing with topological spaces. I don't think we are dealing with their group structure. I think that we will be largely interested in the homology groups of these things, and these give like really nice projective and injective resolutions. Where that's like, I don't really know how to explain a projective or injective resolution without adding a lot of content that's just going to show up later. But like, suffice it to say, this gives us a nice property that I think we'll care about later, if I had to guess. But again, all of that stuff is coming from my intuition in algebraic geometry with homology and cohomology. Here we're talking about the topological space, and this is kind of defining for us like what we can establish maps on in the cell complex. Yeah. Yeah, the appendix isn't actually super helpful. There's some facts in here that are kind of interesting, but it doesn't clarify the notation at all. So I'm just going to move us back to the first chapter because that's, they have at least examples there. So let me cut it down. Okay, so some examples of cell complexes. Just gonna do that. So examples of cell complexes, a one-dimensional cell complex, like x equals x1, is a graph. It consists of vertices to which edges. So vertices are zero cells that we start by building out, and then edges are one cells. I think the number denotes the dimension of the cell. So then vertices are zero dimensional, that makes sense. Edges are one dimensional, that makes sense. In the house with two rooms that I showed earlier on the webcam has visually obvious two-dimensional cell complex structure. The zero cells are vertices where three or more of the depicted edges meet, and the one cells are the interiors of the edges connecting them. So this gives a one skeleton, and then the two cells are the components of the remainder of the space. There are apparently 29 zero cells, 51 one cells, and 23 two cells. And it's interesting that the alternating sum of dimensions equals to 1. What? That's the Euler characteristic. That's Interesting. Yeah, so the Euler characteristic is the number of even dimensional cells minus the number of odd dimensional cells. And apparently, as a theorem in chapter 2, the Euler characteristic of a cell complex depends only on its homotopy type. So the fact that the house with 2 rooms has the homotopy type of a point implies that its Euler characteristic must be 1, no matter how it's represented as a cell complex. That's really fascinating. Okay, that's like a really neat example. I wish I could draw the house.
Wait, what was the Euler characteristic again?
So the Euler characteristic is the sum, the alternating sum. It's the number of even cells minus the number of odd cells. Euler characteristic is
But isn't that always 2?
no.
No.
Like for example, in graphs, if you had a graph that had like one vertex and then a bunch of nilpotent edges, then you could have like this would have an Euler characteristic of 6. No, it would have an Euler characteristic of -6 because 0 is even, sort of. But would it? Can you hold on? That's a good question. Maybe there's I don't know if you can have nilpotent edges like that in topology. So maybe you do have to do this. In which case you have 1, 2, 3, 4, 5, 6. 6 even cells, and then 1, 2, 3, 4, 5 minus 5 edges. But we could also add in like 3 more edges, 4 more edges. But 5 edges, wow, I can't count. And then this would be 6 minus 10. Right? And that would be the Euler characteristic. So yeah, definitely not always 2.
Okay, that's new for me.
Yeah. Let me make sure. Yeah, awesome. Okay. So the sphere has the structure of a cell complex with just 2 cells. So as an example 3, viewing the sphere Sn as a cell complex. Sn is the disjoint union of E0 coproduct En. And this is attached by basically the previous sphere. Maps to, or I guess it's not even in equality. It's like the previous sphere maps to E0, and then the next layer up is the disk D1 mapping to so as Sn minus 1 or Sn maps to E0 coprod D1, I think. This is equivalent to regarding Sn as the quotient space. Oh yeah, this is literally, this is exactly what I wrote. Kind of dn mod the boundary of dn. Right, because like what this does is adds like the boundary of d to dn minus 1. It's like picturing this. If you have a circle and you want to turn it to a sphere, you add the boundary of like the other disk that you add in another dimension and rotate it. I can't draw a sphere. It would really help if I could draw a sphere. But one can imagine a sphere. Maybe I can. So see how like if we had a flat circle, like D1, then we add this as like boundary D. And then that gives us the sphere of dimension 2. Does that make sense?
Yep.
Okay. Yeah, so then example 4, real projective space. So it's basically all of the lines through the origin in Rn+1. And so you can think of this as like equivalence classes of vectors under scalar invariance. Real projective space is the quotient space of a hemisphere with antipodal points identified. So it's kind of like a quarter sphere. I think in this setting, no, it definitely isn't a quarter sphere. Certainly not even a half sphere. So, hold on, I'm very interested in this example. So, real projective space is all lines through 0 in Rn+1. But we can identify this. Oh, it's topologized by Rn+1 minus the origin under V is equivalent to lambda V for vectors V and scalars lambda. So the real projective space is basically the n-sphere mod by the relation V is proportional to minus V. So it is the hemisphere. That's right. And this is equivalent to saying that real projective space is the quotient space of a hemisphere with antipodal points of the boundary identified. So since the boundary of the n hemisphere are projective space of dimension n-1, we can just kind of keep attaching n spheres to this hemisphere. And so the cell complex structure has basically the union I equals 0 to n of e to the I cells with one cell in each EI. So like projective 0 space is just the line of unit length. But then to turn the line of unit length into projective 2 space, or projective 2 space, no, 1 space, projective 1 space, to get like the unit circle, like lines to the unit circle, then you add in like another unit vector. And then you can complete a basis with that using the discrete group of motions. Is this making sense?
Sorry. Yeah.
Okay. Yeah. And then I won't justify this because this has a really long justification, but basically complex projective space, which I'll denote by this, complex projective space, is the union I equals 0 to n of e to the 2I. And I'll leave that to anybody watching this to kind of figure out in their own time. So after all these examples, we now return to general theory. So each n cell in a cell complex has a characteristic map that we've kind of already talked about. So remark, each cell E alpha n in a complex X has a characteristic map like so. 5 alpha defined from D and alpha to X, which extends the attaching map 5 alpha, which we defined here to be taking things from the n-1 sphere to the n-1 complex. And so we extend this from the n disk into X. And then n is a homeomorphism. From the interior of dn alpha onto en alpha. And this makes sense, right? Like we're thinking of each en alpha cell complex as like basically an extra unit disk kind of thing. Namely, we can take 5 alpha to be the composition that we described above, where the middle map is the quotient defining xn. So it's this one. This thing. So this middle map is the quotient map defining x to the n. For example, in the canonical cell structure on the n sphere described in example 3, which was just the n sphere, a characteristic map for the n cell is the quotient map collapsing the boundary to a point. For projective n space, real projective n space, a characteristic map for the cell EI is the quotient map from each disk of dimension I into real projective space of dimension I, which identifies the antipodal points of the boundary. So like, I guess the thing I'm kind of struggling to understand is like what the point of the characteristic map is. Is it just to like have one? I don't. Let me Google this. Let me Google what the heck is the point of the characteristic map and see what
we'll find out later in the book.
Yeah. What is the point of a characteristic map? Algebraic topology. All right. It defines how the cell is attached to the rest of the complex. Okay, this is what math stack exchange is for. Yeah, so basically they provide the glue to build complex spaces from simpler cells. So from each n cell, we have a characteristic map which takes the closed end disk into X, and then it's a homeomorphism from the interior of the disk to the open cell, which is like the cell's interior, and then its restriction on the boundary becomes the attaching map. Okay, I'm really starting to see how algebraic topologists came up with homology like that. Okay, this is making a lot of sense. And they help define the weak topology of a CW complex, ensuring that a set is closed if and only if it intersects the closure of each cell in a closed set. That's really helpful. Okay. So yeah. Any questions on that explanation?
Not really. I really want to read the book and
Yeah.
see the myself. Like I'm a little bit confused with certain stuff, but like I think it's better if I read.
Yeah, I think we're gonna definitely take a slower pace than I had thought. And for no other reason than this book just has a lot of words. Yeah. So I'm just gonna write down the point of the characteristic map is it tells us how to glue together spaces. Thrust. The characteristic map of E alpha n tells us how to glue in alpha to dn. Okay. I want to get through a little bit more of like defining things. I don't know. I feel like it actually looks like this whole thing gets a whole lot easier in like a page. And it also ties back into stuff that we're familiar with because it gets to homotopy equivalence. So a subcomplex is a subcomplex of a cell complex is a closed subspace that is a union of cells of X. Since A is closed, the characteristic map of each cell in A has image contained in A, and in particular, the image of the attaching map of each cell is contained in A. A pair consisting of a cell complex X and a subcomplex A will be called a CW pair. So, definition, a pair X comma A, where X is a complex and A is a subcomplex, is a CW pair. So for example, each skeleton XN of a cell complex is a subcomplex. So like for example, like real projective space K contained in real projective space N is a CW pair. There are natural inclusions, but subspheres are not necessarily subcomplexes in its usual cell structure with just two cells. However, we can give the N sphere a different cell structure in which each of the subspheres is a subcomplex. It just changes the way that we like identify our induction to build out the complex. The infinite dimensional sphere. Okay, man, that makes a lot of sense. That identifies antipodal points is a cell complex. The 2-to-1 quotient map of the infinite dimensional sphere into infinite dimensional projective space identifies antipodal points of S infinity. Yeah, no, that's fine. I'm okay with that. That's fine. Identifies the two n cells of S infinity to be the single n cell of projective space. Yeah, that makes sense. because it's like copying over projective space twice
Mhm.
in infinite dimensions. That's totally fine. I'm okay with that. Yeah, all right. um, it's really funny whenever I go to visit my girlfriend's parents, who are very very nice, very kind, and listen to a lot of the math BS that I am learning.
Mhm.
Um, they'll always like be polite and ask me like, oh, well, like what are you working on? What are you learning about? Um, yeah, dinner around Christmas time is going to have to do with yeah. So there's this thing with like infinite dimensional spheres being able to be constructed of like double projective space in infinite dimensions. That's gonna make for
Yeah, no.
I'm probably gonna do
Are
that.
they STEM majors or?
No, they're just very kind people. Um, um,
It's very hard to tell about math with math people.
yeah, it's one of those things. So this is kind of a tangent, but I was thinking, I read this paper recently about coffee and like how you carry it. Like I don't know if you've ever carried coffee, but like if you are just walking forward, the mug will like spill, up and down, and it's very frustrating. I've always thought. But basically with the way Fourier series works, fluid mechanics are determined um, in no small way by second order partial differential equations. And those are solved with Fourier series, which are sums of periodic functions. And so this guy, I don't know at what university, well, this guy came up with a paper where basically he said that the optimal way to carry a coffee cup is to move it up and down while you're walking, because basically, as long as you time it right, you will create a standing wave. And that like is the equilibrium solution um, to the partial differential equation for a bounded disk of roughly water-like fluid. Um, which I think is just a fascinating thing. And I was telling them about this over dinner the other day, and I think that was like the first thing I've talked with them about that like finally clicked as like I explained it well enough that it made sense to somebody.
Mhm.
I felt very proud. But yeah. Um, So, finishing up this section, in examples of cell complexes given so far, the closure of each cell is a subcomplex, and more generally, the closure of any collection of cells is a subcomplex. Most naturally arising most naturalized, wow. Basically, cell structures usually have this property, but it doesn't need to hold in generality. For example, if we start with the one sphere with its minimal cell structure and attach it to a two cell by a map of a one sphere into a one sphere whose image is a non-trivial subarc of the original sphere, then the closure of the two cell is not a subcomplex since it only contains a part of the one cell. So like if we attach
By the
is
way, I
this
can't see your screen.
oh yeah, that would help. Thanks. um yeah, share screen. Yeah, so what I was saying, so if this is our one sphere, that is a one sphere, right? No, this is a one sphere because we start with point, then we extend it to an arc, and then if we take a non-trivial subarc like this, and we try to identify it to yeah, because it's yeah, attach it to a two cell, which is going to look something like this, and then we attach like that part of the arc. This is a closure, which is not a complex. Like it doesn't build out the whole like end disk, right?
Mhm.
Um, because it only contains part of the one cell. Um, so operations on spaces. Cell complexes have a nice mixture of rigidity and flexibility, with enough rigidity to allow many arguments to proceed in a combinatorial cell-by-cell fashion, and enough flexibility to allow many constructions to be performed on them. Here are some of the constructions. So, constructions on spaces. So products, if X and Y are CW, then X product Y is CW. For example, the cell structure on the torus, which is the one sphere producted with itself, is a natural cell complex. The topology on a general product of cell complexes is slightly weaker than the product topology, with more open sets than the product topology has. Though the two topologies coincide if either X or Y has finitely many cells, or if they have countably many cells. In practice, this doesn't show up. Okay, nice. Quotients. If X and A is a CW pair, then X quotient A is a CW complex. And then they're attached by the cells of XA are exactly X minus A plus a zero cell, which is the image of A in X quad A. So basically, we take the things that are already a cell complex and then we reattach the other stuff somewhere. For a cell attached by phi, this just factors from the n-1 sphere to the n-1 complex into the quotient. I recommend anybody watching this reads through the thing a little bit, the textbook. A new word that I've never seen before, suspension. For a space X, the suspension Sx is the suspension. X is the quotient obtained, or quotient of X product, the unit interval, collapsed. Whoa, wow, collapsed to X at 0 and X at 1. Okay, this is like the most natural construction ever. As a motivating example, X is equal to the sphere, the n sphere, and then Sx is equal to Sn plus 1 with 2 suspension points. So like if you have your original n sphere, consider like S1, then you have 2 suspension points, 0 and 1. that determine like a diamond. Whoa. Like that. And so this is like basically a double cone. If X is a CW complex, so are its suspensions. And what is CX? Oh, CX is the cone. So I guess this is an important definition because they give it a notation. CX equals the cone, which is X product the unit interval mod X product 0. And then as a theorem, if X is CW, so is SX and CX. Suspension becomes increasingly important the farther one goes into algebraic topology, though why this should be so is certainly not evident in advance. One especially useful property of suspension is that not only spaces but also maps can be suspended. Namely, no, maps can be suspended. Maps can be suspended. Namely, f from x to y suspends to sf from sx to sy. Which is the quotient map of f idx from, or no, idi. Let me see, do I want to get through join meet, wedge sum, smash product? I think that this is enough for now. We can come back tomorrow and talk about the other operations on spaces. So tomorrow we'll talk about two special operations called the join and then the wedge sum or the meet and then the smash product. And then we'll talk about criteria for homotopy equivalence and hopefully some other stuff, homotopy extension. So yeah, and then we're through chapter 0. So maybe we can even get into chapter 1 tomorrow. That would be great. I would be very happy with that, but I don't want to rush it. So yeah. So anyway, good deal. Awesome first session, I feel like. I'm excited to go through this book. This has been a lot of fun so far. I think topology is one of my favorite classes I've ever taken. So I think that algebraic topology combines my two great loves, algebra and apparently now topology. And there's actually there's a lot of geometry in here, and I can see kind of the overlap between AG and AT. So yeah, I'm gonna go ahead, stop the recording, and yeah.